All right. Sorry, folks, we had a computer breakdown, and I kept on teaching. We're going to pick up where we left off, and this is now on, let's go from current slide, and then advance to, okay, here. All right, there was a power rule. I don't think I had shown that on the slide, had I? Oh, yeah, we had, hadn't we? Yeah, okay. And then we did, yeah, we were on this slide, I think, when it died. And here was example 2. If we function f of x equal x cubed, what is its derivative? For the power rule, exponent times coefficient, 3 times 1 is 3, and then reduce the exponent by 1, x squared. Okay? G of x is equal to cube root of x, d by d, that. Now, notice what they did. They didn't show you they were going to do it. They rewrote g as g to the is equal to x to the 1/3 power. Rewrite your radical as a power of x. Okay? And that's what they did without really defining it or showing you. And then you do the same thing. 1/3 times 1 is 1/3. X to the subtract 1 from 1/3, you get minus 2/3, which is a perfectly good answer. Or you can write this as 1/3 times x to the 2/3 power. Another perfectly good answer. Okay? So, both of those are good. And here's y is equal to 1/x squared. And again, you rewrite this to be in power form. That would be x to the minus 2. That's why they wrote it this way. And d by dx of x to the minus 2 is exponent negative 2 times coefficient 1. That's negative 2 times x. So we drop that by 1. Negative 2 minus 1 is negative 3. Okay? So that's a perfectly good answer. You could have written that as negative 2 over x to the 3rd or negative 2 over x cubed. All three of those are perfectly good answers. Any questions on those? We did them otherwise. Okay. And that 2c, notice that before differentiating, and we did it in 2b too, or not 2b too, okay, and that was rewrite your given function in power notation, x to the some power. We did it in 2b, we did it in 2c, okay. And that gave you that and simplified. All right. Now they're skipping example 4, and that's, no, 3 and 4. So let's go back to 3. All right, and let's do 3. I started that, wrote it on the board. Now let's not write on my screen with that, okay? We won't do that. And you want me to go and erase that before it dries out any more than it has? You don't need this any longer? These markers dry out awfully fast, and then they're very hard to erase. Okay, I'll try to get that cleaned up after class. If I move too fast, my head hurts like crazy, so I'm going to try to slow down a little bit. All right, so let's do, and I've got to get my pen reclaimed here. All right, here's example 3. Find the slope of the graph of f of x is equal to x to the 4th. Okay, we want to find the slope of the graph for each value of x. So the first of these is going to be when x is equal to negative 1. Okay. This is where it started messing up before. The pen got really slow, and I would write on the screen, but nothing would show up, and then it crashed. So it just got real slow again. Now, how do you do this? What you want to do is find the slope of the function at that point. How do you find the slope? Take a derivative, exactly. Okay, now do you plug into x equal minus 1 first and then take a derivative? No, because that's always going to give you a constant, the derivative be 0. That's probably not going to be the case. So you take the derivative of x, the function with respect to x first, then you plug in your x equal -1. Okay? So let's first do f prime of x. And what would that be? To the third power. Got it. Now we can plug these values into each of those. So f prime at -1 would then be what? Okay. The 4 times -1 to the third power, which is -4. Perfect. You see it? Is that what you said?
Oh no, I said 64.
What's that? No, you're not cubing the 4. The 4 is the constant out front. You're only cubing the -1. I'm sorry. And -1 cubed is -1 times -1 times -1, which would be 1 times -1, which is -1 times 4, -4. Sorry about that. Okay? So the B part here is asking what is the slope when x equals 0. So x equals 0, what's your slope? F prime of 0 is equal to 0. Now that one did come out 0. How about the C part? When x equal 1. F prime of 1 would be F prime of 1 would be 4. Perfect. Okay. Okay. Because you just plug in 4 times 1 cubed. 1 cubed is 1. And that gives you that. Now, you've done it. All they ask for here, find the slope of the graph. That's your first derivative. But then they draw a graph to show you. Now, my graph is not going to be quite as pretty as theirs, maybe. But here it is. It's a quartic function. That's what we're graphing here. And that's going to be at 0, 0, at 1, 1, okay, at -1, 1, because when you raise -1 to the 4th power, it's -1 times -1 is 1, times -1 is -1, times 1, -1 again is +1, okay? And then it goes up astronomically from there. At 2, that would be 64, okay? 2 times 2 is 4, times 2 is 8, times, no, 16, okay? Okay, I can't get that on scale. So what it does is it goes up very fast here, flattens out here, and then goes up very fast there. That's sort of what it looks like, okay? Now, I don't have it very well done, but here's x equal -1, the slope of the tangent line there, very steeply -4. Slope of the tangent line down here at 0, sure enough, is 0. And slope of the tangent line over here is, again, very steep, but now going up, and that's a +4. So this is a negative slope downward, -4, 0 here, +4. So my picture isn't very good. Theirs in the book, a little bit better. Okay. So go for it. Now, let's move on to example 4, which they didn't show in the slide set either. So let's erase all this ink. Any questions before I erase it? Okay. Too bad. No, I'm just kidding. Okay. Example 4. Now, both of these examples, 3 and 4, notice there the little red line here. See larsoncalculus.com for an interactive version of this type of example. And maybe that's why they didn't show it on the slide, because you can go to interactive, larsoncalculus.com and see it a lot better than what you would even on the slideshow, because you probably get to hear about it as well. All right, here's example 4. Find an equation of the tangent line of this function. f of x equal x squared, an equation of the tangent line when x equal -2. So, what do you think the equation of a tangent line is going to look like? Key word in there is line. What is the equation of a tangent line going to look like? Okay, it's going to have a slope in it, isn't it? So this equation of the tangent line will have an m for slope. Second? I wouldn't. I would just write it as y is equal to mx plus b, wouldn't you? That's going to be a line, isn't it? Always a line. And in the form I like best, called the slope-intercept form. And like Clark already said, it's got to have a slope. So once we figure out what the slope is, we got half the battle won, right? How can we figure out the slope of that function at that point? Second? Not yet. No, you're close. What do you have to do first? What gives you the slope of a tangent line? Yes, the derivative. This reminds me of when I was teaching Math 100, and I was, most of the problems there dealt with factoring. So what I tell the students, say, when I ask in the class, what's the F word, you better say factor, okay? So, and most of the time they did, I think. Well, out loud anyway. Okay, so, it's not that funny. Okay, so, now when I say, what do you do? The answer is not factor, it's going to be take a derivative, okay? So I guess this is what we'll say for this case. I don't know if any of you go to church or not, but a lot of churches nowadays have children's church, okay, where all the little kids come up and someone talks to them and stuff like this. And usually the pastor or whoever it is that's running it will ask some question. And the kids sit there not really knowing what to do. So usually one will pop up and say, Jesus, okay? Because most of the time in church, if someone asks a question, especially a pastor-type person, he's never going to say that's the wrong answer, No, that's always the right answer. So your Jesus in here is going to be, take a derivative, okay? When I ask, what should you do? Rather than say Jesus, say, take a derivative, okay? That'll get you through Cal 1 most of the time. Okay, so what do we do? Take a derivative. And what would that be? What? Jesus, okay, never mind. What? 2x, okay? So how do we get our slope? Plug in a -2. You're absolutely right. The slope is f prime of -2, which will be -4. Ding, ding, ding. We've got the m part. So the equation for your tangent line is going to be a -4x plus b. Okay? Now, we still don't know what the b is. And there's not going to be a really easy way to do that, but it's not that bad either. And this is something, when Elijah said it, I said, you're really close. Because one thing you do know is what point you're at when x is equal to -2. So let's plug in this, because what's your f of x? Y. And there, -2 is going to be your x. So you can give me the xy point that's at that place. Okay? So let's do that too. Let's do f of -2. And what would that give you? 4. Okay? Now, we have a point. What's your point? It's going to be -2, 4. When x equals -2, y is 4, right? Now, let's plug that into your slope. Because guess what? The tangent's got to touch that point, right? That's a point on the curve, on the parabola, but it's also going to be the point where the tangent line touches, right? So now we have a slope. We won't get the y-intercept, but you can get the value. Because let's plug in a 4 for the y is equal to minus 4, that's your slope, times your x, which is negative 2, plus b. And what does this give you? 4 is equal to negative times negative is positive 8 plus b. And now, subtract 8 from both sides, and that gives you negative 4 is equal to b. There we have it. Now we know this equation for the tangent line. It's y is equal to negative 4x minus 4. Just happens to be the same value for m and b. That's not now always going to be the case. Don't even think it will be. But that's how you do it. There's your equation for the tangent line. Now, probably would help us to draw the graph on this one too. It's going to be pretty crowded, so I can either remove all this from the screen, you fill me in on later, or I can graph it here. So you tell me, which would you rather? Leave it up here or erase it first? Erase it. Okay. Y'all have to remember to tell me. The function is f of x equal x squared. That's going to be pretty easy. We got to remember what the point that we're interested in, negative 2, 4. And then we got to remember what the slope is, and we'll deal with that. So you got all that written down, right? Yep. So let's erase that, and let me draw the graph. Okay. 0, 0 is on that function because it was, remember, f of x equal x squared. Okay? 1, 1 was on the function because when you plug in 1, negative 1, 1's on the graph, right? 2, 4, 2, 3, 4, so that's going to be up here, and negative 2, 4. And 3, that's off scale, but it's going to be somewhere up here. Here is the graph of that parabola. Pretty something like that. Okay? Not really all that pretty. And here is the point in question. Negative 2, 4. Wasn't that the point? Okay, so we did that right anyway. Okay. Now we want to know the slope, the equation for the tangent line. Well, here's a tangent line here doing something like this. I can't draw very well, but it's going to intersect down there. It's going to have a slope of, what was the slope of it? Negative 4. And it looks like it's y-intercept. Yeah, it looks like it could be right around there, like negative 4, right? That looks like the equation of that line. So that line would be y is equal to minus 4x minus 4. Slope negative 4 at that point, and y-intercept looks like it'd be negative point at that point. Negative 4 at that point too. My picture isn't pretty enough to tell you that, but that's what it would be. See how that works? All right, good deal. If you don't see well enough, go to Larson Calculus for an interactive version of that type of an example. All right. Any questions before I move on? Okay, this was example 2, so we'll move on past that. All right, now let's go to the constant multiple rule. Okay? And here's what that is. So let's say f is some differentiable function. You don't know that except they're telling you it is. Okay? And c is some real number. Any real number. Positive, negative, fraction, decimal, rational or irrational, square root of 3, negative 4/3 square root of 3. You have any real number. Well, if f is a differentiable function and c is some real number, then c times f. Multiplying a differentiable function by any constant, no matter how bizarre the constant is, is also going to be a rational function. And what's more, d by dx, or the derivative of that new function, c times f of x, because that's just a constant, pull it on the outside. And then it's c times f prime of x. So d by dx of f of x is f prime of x. Pretty simple rule. I'm so glad it's a simple rule. That's what I was hoping it was going to be, something really simple, and that's what it is. So if you have a constant of a differentiable function, constant times a differentiable function, you can just pull the constant out, take the derivative of the differentiable function, because it's differentiable, and then multiply that constant by its derivative. Wow. Pretty straightforward. Now they do show a proof here, using your limits. I know you're wanting to do that, aren't you? Okay? So follow that in the book, and you can see every step, it works like a charm. Okay? Now, I've already been saying that, whether you call it or not, because I've been saying, times your coefficient, that was a constant. All those coefficients happen to be 1. But I've already been saying, you just multiply by that. So, anyway, let's do, I really don't like it. All right. There's your function. Y is equal to 5x cubed. What is its derivative? 15x to the second power. Exactly. dy dx would be d by dx, said it again, of y, which is 5x cubed. Pull the 5 on the outside, then take the derivative of this, which means 3 times that, and that 15x cubed. Okay? Now that's just an extra step that if you just did it the way I said, just do 3 times 5 is 15, drop that by 1. It does exactly what your constant multiple rule says. So I found it so much easier just to do it that way rather than going through 2 or 3 steps to get there. But it gives you the same answer, 15x squared. Make sense? All right, let's do this one. What do you better do first? No, not yet. Oh yeah, you choose this answer. Yeah, I understand, but what do you better do before you take the derivative? Okay, yeah, get that variable out of the denominator. It's a rational form now. How would you write that?
2x to the negative 1.
That's it, 2x to the negative 1. And you see, they did it. They didn't tell you to do it, but they did it. And then what will you be? Now take your derivative. What would that be? Anybody? A little louder?
Negative 2x.
To the negative 2. They took the 2 out, blah, 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 and that gave you negative 2x to the minus 2, and then they wrote that as negative 2 over x squared. They get a little carried away with the constant multiple rule. Just multiply the exponent by the coefficient. Oh, by the 10 o'clock scholar, why do you come so soon? Okay? All right. Justin's here. Good deal. Anyone else come in since I called off? Okay. We're on page, goodness, I'm getting dizzy. 113, example 5, bottom of the page. Okay? We've just done A and B. Now we're going to do C. All right. What do you reckon we're going to do with that? There's f of t is equal to 4/5 t squared. We want to find this derivative. What will this derivative be? Can you see? I know I'm blocking you here too much, but it's not that funny. Now, what? What would that derivative be? What's your coefficient?
8t
over 5. We count that as 4/5 times 2 would be 8/5. Okay, 8t over 5. That's it exactly. You write that as 4/5 t squared. Take the 4/5 on the outside. Take the derivative of t squared. Boy, this is a long way to do it, That would be 4/5 times 2t, which is 8/5 t, yes. So much easier to do in my mind is to do 2 times 4/5 is 8/4 times t. Drop the exponent by 1. Make sense? Yay or nay? All right, good deal. All right, let's move on to D. What would you do first?
Rewrite.
How?
2 times x to the 1/2.
Yes, 2 times x to the 1/2. And then you take the derivative of that, and what do you get? I wish I could write this down, but if I write it down, you see the answer. I don't want you to see the answer. Okay. So you write it down.
That would be 1x negative 1/2.
Excellent. There you have it. 1x to the negative 1/2. And then if you wanted to write that in radical form, that would be 1 over the square root of x. Now, in this problem, this is good for all real numbers x. This one can't be good for x equals 0 because the original problem wasn't good for x equals 0. This would be for all real numbers x. This, even though the original problem is good for all x's greater than or equal to 0, can't be a negative, right? You can't take the square root of a negative number. So x's have to be greater than or equal to 1, but as soon as it goes downstairs, greater than or equal to 0, it can't be equal to 0 anymore. That would have to be greater than 0. So you always have to sort of keep that in mind. If you have square roots or any even root, your whole problem can't be negative. What's inside the radical can't be negative, but it could be 0. But once it goes downstairs, it can't be 0. Okay, so that will only be good for x's greater than 0. Okay. I think there's an E here, so let's see if we can get E here. What would be the first thing you'd want to do on that?
Rewrite.
Rewrite, and how will it rewrite? Say again?
That's kind of tough.
Yeah, that one's a little tougher. First, what's your coefficient?
1/2.
1/2. Okay, so it's 1/2. Rewrite it as 1/2 times. Now, we got to get that as a power of x.
So that would be x to the 2/3.
That would be 1/2 times 1 over x to the 2/3. But you still got the x in the denominator.
Oh, so it would be negative.
2/3. Yes. Okay, it would be y is equal to 1/2 x to the minus 2/3. Does everybody see that? I wish I could write it for you, but that would give away the problem here because you'd see it. So d by dx, or dy dx, would then be, if y'all are writing this out, right? If you had 1/2 x to the minus 2/3, you take the derivative of that, what would that be? Okay. 2/3 times 1/2 would be black and blue boxes. Yeah, it'd be 1/3. The 3 is another number, right? Okay. So 1/3 or negative 1/3, because that was a minus 2/3. So it's negative 1/3. There's a negative 1/3. Now what's your exponent? It was.
That would be 3/5.
Okay. It's negative 2/3. Then subtract another third from that. 1 from that, which is another 3/3. So negative 2/3 minus 3/3 is
4/3.
5.
5.
Minus 5/3. So that would be negative 1/3 x to the minus 5/3, or if you want to write that back in and they're not being very consistent here. If you want to write it back down here without a negative exponent, it would be negative 1/3 times x to the 1 over x to the 5/3. But if you started off in radical form and wanted this in radical form, and here's another perfectly good answer, okay, that probably WebAssign would not recognize, but to me it would be as legitimate, if not more so. Negative 1 over 3 times the cube root of x to the 5th. See, that's the form they gave you the original problem in, so why not give your answer in that same form? Okay? Now, again, if I were doing this now, I think I will do it since we've got room here. I would have rewritten this problem as y is equal to 1/2 x to the minus 2/3 power. And again, it's a minus radical because your x is in the denominator. Your numerator for that is going to be the power of x. Your denominator is going to be the index of your radical. So that's what made it this. Okay? And then using my modified rule, it is the constant multiple rule, but it just makes it so much easier. Exponent times coefficient. That will be a negative 2/3 times a positive 1/2. The 2's will go out. That will give you negative 1/3. Y prime would then be negative 1/3 x to the, reduce that by 1. Well, minus 2/3 minus another 3/3 would be minus 5/3. Okay? And then you could write that as negative 1 over 3x to the 5/3. That's how they did it. But since your original problem started in radical form, it would seem like to me you would write this as negative 1 over 3 times the cube root of x to the 5th. Again, the numerator is your power, the denominator is the index. Okay. Now, probably WebAssign would have only recognized that answer. This answer's, well, that's the same. That answer's perfectly good. That answer's perfectly good. All those answers, perfectly good, correct answers. But of course, a computer program can only recognize one most of the time. They don't seem like they have artificial intelligence in these packages yet. In fact, I wonder if there's any intelligence in the packages yet. I'm sorry, I'm kind of negative, am I not? Okay. There is another one, isn't there? I didn't notice. Okay. Oh, and by the way, I'd like to say this too. Notice, remember this one? X is, in your original problem, had to be greater than or equal to 0, but in your derivatives, it just had to be greater than 0. You couldn't even be equal to. This one, okay. X's can't be 0. Okay? Now, you could conceivably have a negative number in here, but x squared is always going to be positive. And you can take the cube root of any number you want to. You just can't take it to 0. So in this problem, it starts off with x can't be 0. Okay? And your answer over here, same deal. This x could be negative because x to the 5th would be a negative number, but a cube root can take a cube root of a negative number. It's just x can't be 0. So you don't have to worry about that, but it's not a bad thing to think about. Let's see if alpha, oh yeah, alpha is on there. So let me erase all this. I'm surprised they're into the background here. All right, here's another function for you. Alpha is equal to minus 3 halves x. What would be its derivative? Second. Minus 3 halves, that's it. Okay? Because your exponent is 1. 1 times negative 3 halves, negative 3 halves. Drop the exponent by 1. X to the 0 is 1. Okay, yeah. I like that one. It's just the coefficient of your x. Okay? Just like it always was. Okay? You don't have to factor out the minus 3 halves first, but you could if you wanted to. All right, good deal. Now, the constant multiple rule and the power rule can be combined into one rule. Oh, what a clever combination this is. Rather than doing 2 or 3 extra steps, here's what you do. d by dx of this function, c times x to the n, that's a constant multiple times a power function, right? Would be the exponent times the coefficient, drop the exponent by 1. Oh, I'm glad they thought of that. Okay, that's what I've been trying to get you to do all along. It's just so much easier than doing 2 pieces separately. Works pretty nicely, doesn't it? Okay, good deal. All right. They do have example 6 with this that they're not showing, so let's go back. Let's do it right here. I think we've got room. Oh, goodness, yes. Okay. All right, let's do example 6. They didn't show this on the slide set. Neither do they show it at their larsoncalculus.com. So let's do this. Strange. They entitled this Using Parentheses When Differentiating. Let's see if that's necessary. Here's the A part. Original function is y is equal to 2 over 5 over 2x cubed. Okay? What would you think my first suggestion would be? Rewrite it. And how would you rewrite that?
5 times 2x negative
3. Okay, say that one more time.
5 times 2x negative 3.
It's actually 5 halves. The 2 doesn't move upstairs. 5 halves, that's your coefficient part, x to the minus 3. You see that? Don't mess with the coefficient. Leave it alone. 5 halves. Move this, take that, and write it in exponential form. Out of rational form into exponential form. Okay? That's your rewrite. Now, they put it in parentheses. I don't see why you need to, but you could if you wanted to. Their next is to differentiate. What is dy dx? Negative 15 halves. There's more. X to the negative 4. Perfect. Now, what they call simplifying, and to me it's nothing any simpler, but getting it back into a similar form of what you first had, that then could be written as minus 15 in the numerator, 2x to the 4th in the denominator. Okay? It just is moving. Since you started with this in rational form, let's give the derivative in rational form as well. Now, if you're worried about what values in your domain, obviously x can't be 0, but any other value it could be. Well, that's true here, it's true there. Okay. You can't ever divide by 0. You can divide by any other number you want. Okay? Let's see if that's what they got. Negative 15 over 2x to the 4th. Very good. B. Y is equal to 5 over a 2x cubed. Okay. Interesting. Don't know why they would choose to write it that way. There's several ways you can approach this. What would you do? Help me out here. It's got to be your first step here. Somewhere along the way, anyway. Okay, and how would you rewrite it?
same as the last one.
Not quite, because you do have parentheses here. It's not. See, this is 2x cubed. The 2x cubed. This is 2 times x cubed. Remember your, please excuse my dear Aunt Sally. I don't know what she did, but whatever she did, please excuse her. Okay. You do your exponent before you multiply, unless you have parentheses, and you parentheses first, then you exponentiate. Okay. So actually, how I would do this, I'm pretty sure it's not what they're getting at, but I would do it like this. I'd say that is 5 over 2 cubed is 8x cubed. Now I would proceed as we did before. Let's rewrite that now. What would that be? 5/8 x to the negative 3. Now I would differentiate it. dy dx would equal say again? Negative 15/8, which can't be reduced, unfortunately, x to the negative 4. Okay? And then if you wanted to rewrite that, you could write it as minus 15 over 8x to the 4th. Now, let's see how they did it. They did come up with that answer, and yeah, they didn't show you how they rewrote it, but they did rewrite it correctly, and then from there on was about the same. Okay? So I would, yeah. There is another way to do it, but we don't have another rule in our pocket that you could do it that way. So we won't worry about that yet. We'll worry about that tomorrow, for tomorrow is another day, said Scarlett. Okay. Let's do number C. Y is equal to 7 over 3x to the minus 2. What would you do first? Rewrite. How would you rewrite that? 7 over 3. Second? X squared. Ding, ding, ding. You got it. Okay. And that's going to be a pretty easy one to do your derivative of. dy dx is going to be what? 14/3, which can't be reduced, x. Done. I guess you could write this also as 14x over 3. That's another way you could write it, which would be perfectly right, which is what they chose to do. But why? This form was just as good, but guess what? Good old web design is only going to recognize one of them. Which one? That's up to whoever wrote the program, I guess. All right. Any questions on that? Let's try D. D would be y is equal to 7 over, they like 7s, don't they? Okay, over 3x to the minus 2. I see what they're doing, I think. Now, what in the world would that be? Okay, I think you're right on it. 7 times 3x squared. Isn't that it? You move this whole thing upstairs and drop the minus sign. All right? And that it would be, and you already were a step ahead of me, what would that be? 7 times, I heard you say it, 9x squared, right? You square both of those. And what's 7 times 9? 63x squared. There's all the work of the problem. The derivatives are the easy part. dy dx would be would be, I'm hanging on the cliff. I'm about to fall, huh? What'd you say? 120 what? 6 x. Ding, ding, ding. Done. All right. And that's what they got to. Good for them. Okay? You see how to do those. Okay? Find the easiest way to rewrite the problem. Okay? Do what we tell you. All right. That was example 6. Let's now move to some. Did anyone need that a little longer? Oh, okay. I'm sorry. I thought you were trying to take my picture. Sorry. Never mind. Yeah, she was going to break her camera. Okay, I see it. Okay. Oh, yeah, okay. All right, good deal. Okay. Now let's move to sum and difference rules. Okay? And guess what, folks? Hopefully they're going to be exactly what you're expecting them to be. Here is your theorem which describes the sum and the difference rule. The sum or the difference of two differentiable functions. So you know already that f is differentiable and g is differentiable. What if you're adding those two together? Well, number one, the sum or the difference of those will be differentiable. Given. They give you that. It's got to be. If the two functions are differentiable, the sum or the difference is going to be differentiable. Moreover, what would be that? The derivative of f plus g, or f minus g, would just simply be the sum or the difference of their derivatives. So the derivative of the sum function is the sum of the derivatives. The derivative of the difference function is the difference of their derivatives. Boy, can you get any easier than that. That's exactly what we would hope it would be, and sure enough, that's what it is. Now, Clark's going to want to prove it, and the proof is underneath it somewhere there. With the limits, they will be so much fun to do. Okay, so do that if you would like. And let's us move to example 7. All right, so there's a function. F of x is equal to x cubed minus 4x plus 5. What do you think the derivative should be? F prime of x would be what's the derivative of the first part? 3x squared. There's that part. What's the derivative of the next part? Say again?
Minus 4.
Minus 4. There's that part. And what's the derivative of plus 5?
Plus 1. 4.
That's a constant, isn't it? What's the derivative of a constant?
Oh, 0.
0. Yes, yes, yes. Okay. That would be it. Okay. F prime would be 3x squared minus 4x minus 4. 0. Nice, huh?
So if you don't have an x there, pretty much it's a 0.
Yeah. Well, yeah. If it's a constant, the derivative of a constant is 0. You're absolutely right. Okay. Let's see if we can squeeze in g. There's your g is minus x to the 4th over 2 plus 3x cubed minus 2x. So what would g prime be? Negative 2. X to the 3rd power. There it is. Negative 2x cubed. Plus what? Woo. 3x cubed. What's its derivative? Exponent times coefficient. 9 what? 9x squared. Got it. Anything else? Minus 2. Perfect. Very good. You see that, everybody? Excellent. Okay. Let's see if we can squeeze in C. C is y is equal to, all right, 3x squared minus x plus 1 over x. What's the first thing you got to do with that? Is that in power form? No, it's in rational form. So let's do it. And it's fairly easy to do because that's 3x squared over x, which is?
3x cubed?
No, over x. 3x squared over x.
So it's
Just 3x. Okay, there's the first part. Then?
That's 0.
No, it's not a 0. X over x is?
1.
1 minus 1. Perfect. The derivative will be 0. Maybe that's what you're thinking. And then you got the last term is going to be? It's plus 1 over x, isn't it? It's this thing over x, this thing over x, what's that over x, right? We're rewriting now. We're not taking a derivative. We're just rewriting, okay? But how would we rewrite 1 over x? I don't like that.
1 times x to the negative.
Yeah, x to the minus. Oh, look at that. They wrote it bad. They should have written that plus x to the minus 1. Would you have written it that way? Say yes. Okay, good. Okay. All right? All right. Now let's take the root of that with this being x to the minus 1. What's the root of the first one? 3. Good. Next. 0. Okay. And then the next was plus x to the minus 1. That would give you
Negative 1.
negative 1.
Oh,
X to
the minus 2.
to the minus 2, which would then be the same as negative 1 over x squared. Now they act like you're supposed to know this becomes that. You really aren't. Write that as minus 1 over x squared, then take its derivative, plus 1 over x, plus 1 over, plus x to the minus 1. Then take the derivative and make it minus x to the minus 2, then rewrite it back this way. Okay? Now, since they started in rational form, if you want to get it back to rational form, put this over 3x squared 2. That would be 3x squared minus 1 over x squared. To me, this is sort of ridiculous to do it that way. I would have left it as this answer right here and been perfectly happy with it. There's no real reason to do there, but they did. And it's right. Perfectly correct answer. Just more work. And guess what I am? Lazy. So why do more work? Okay. So I have told you all that, right? I think to be really good at math, you got to be a little bit lazy because you're always trying to find the simplest way to do a problem. Do any of you qualify? Oh, good. Okay. Now, if you're a hard worker, you can still do it. Okay. No problem there. You just have to work a little harder. Okay. Never mind. We didn't get to do D, did we? And we ran out of time. Shame. If the computer hadn't messed up, I want to go and cheat the computer and do it? Okay, let's do it. Okay. Whoa, it didn't show D, did it? We will do D. Wait, I was looking at the wrong one. This is example 7. They only had C. Okay, we did finish. Okay, let me give you a few homework exercises. I know you wouldn't want to leave home without them. So we'll start next time derivatives of sine and cosine function. I think that's where we start next time. Yeah, okay. So your homework exercises here. This is a long section, isn't it? Do number 5. It's at screen. It's at calcchat.com, but it's also at calcview.com. Then do any of the odds, 7 through 25. They're all at calcchat.com. Only 17's at calcview.com. Then do either 27 or 29 or both. They're both at calcchat.com. Only 27's at calcview. And then do any of the odds, 31 to 37. They're all at calcchat.com. 37's at calc. Oh, wait, no. Whoa. We'll stop at 35. Okay? Stop at 35. Because 37 is after we do sines and cosines. Well, let's see. You can also do 39, 41, 43. You can do through any of the odds 39 to 49, because those also are ones like we did. All those are at CalcChat, only 43 is at CalcView. And then you can do 55 and or 57. They're both at CalcChat, only 55 is at CalcView. and you can do 59 and or 61. Okay, I think. Maybe not. Hold off of those. You don't have to do that many. We'll pick up the rest of it. We got plenty of time. Okay. Good deal. Any questions? Good deal. Have a good weekend. Of course, what's going to make it a good weekend? Working a bunch of calculus problems, won't it? That'll certainly do it. And maybe even working on those papers, right? Don't forget your papers. All right.